Hey everyone, and welcome back to the channel. If you're involved in agriculture, you know how crucial it is to understand your crop's health. We talk a lot about NDVI, but what if there was an even more powerful tool, especially for challenging environments like orchards or rice fields? Today, we're diving deep into the Insensitive Pigment Index 2, or SIPI2. This isn't just another vegetation index, it's a game changer for precision agriculture. For years, the Normalized Difference Vegetation Index, or NDVI, has been our go-to. And don't get me wrong, it's fantastic for general greenness and biomass. But when you look at a mature orchard or a vineyard, things get complicated. You have individual trees, shadows, and often ground cover like weeds or grass between the rows. NDVI struggles here. It can get saturated in dense canopies, meaning it stops showing real changes in plant health. Plus, it gets confused by the greenness of weeds, giving you a misleading picture of your actual crop. This is where SIPI2 shines. Unlike NDVI, which primarily measures overall greenness, SIPI2 is designed to specifically assess the ratio of carotenoids to chlorophylls within plant leaves. Think of chlorophyll as the green pigment responsible for photosynthesis, and carotenoids as the yellow-orange pigments. In a healthy plant, these pigments are in a balanced proportion. But when a plant is stressed, whether from nutrient deficiency, water scarcity, disease, or pests, chlorophyll often degrades faster than carotenoids. This increases the carotenoid-to-chlorophyll ratio. And that's exactly what SIPI2 is designed to detect. Its unique formula, using specific reflectance measurements from the near-infrared, green and red-edge spectral regions, is built to capture this critical shift. And increasing SIPI2 value signals an increase in this ratio, acting as an early warning indicator of plant stress, often before visible symptoms appear. This structure-insensitive part of its name is key. It minimizes the confounding effects of canopy architecture and background noise, allowing it to focus directly on the plant's physiological state. Now, you might have heard of the original SIPI. It's important to distinguish between SIPI and SIPI2, as they are not interchangeable. The original SIPI used a blue band in its formula, while SIPI2, our focus today, substitutes that with a green band, around 505 nanometers. This seemingly small change is significant. The blue region is more susceptible to atmospheric scattering and strong absorption by both chlorophylls and carotenoids. The green region, on the other hand, corresponds to the characteristic reflectance peak of healthy vegetation. This means SIPI2 offers different sensitivities and responses to stress, making it particularly relevant for modern agricultural applications. So, how do we get the data to calculate SIPI2? It all comes down to remote sensing platforms, satellite-based monitoring. For large-scale monitoring, satellites like the European Space Agency's Sentinel-2 are fantastic. They offer consistent revisit times, providing public multispectral imagery. While Sentinel-2 doesn't have an exact 505 nanometers green band, its band 3, 560 nanometers, serves as a close proxy. Commercial satellites like Worldview 3 offer even higher spatial resolution and more precise bands for SIPI2 calculation. The key here is understanding that some approximations are made, and resolutions may need to be adjusted. Drone-based multispectral imaging. For on-demand, high-resolution insights, drones equipped with multispectral sensors like the MicaSense Altum are becoming indispensable. These sensors provide centimeter-level detail, perfect for specific field sections. Again, the green band might be a proxy, but the detail is unmatched. Hyperspectral frontier. And then, for the ultimate spectral fidelity, we have hyperspectral sensors. These capture hundreds of narrow contiguous bands, allowing for the most accurate SIPI2 calculation at the precise wavelengths. A critical step, especially with drones, is radiometric calibration. This process converts raw sensor data into meaningful reflectance values, ensuring accuracy and comparability of data over time and different lighting conditions. It's the difference between guessing and knowing. Now, let's get to the practical applications, starting with orchards, vineyards, and other perennial crops. These environments are a perfect fit for SIPI2 because of their complex, discontinuous canopies. Remember that issue with NDVI getting confused by weeds and shadows? SIPI2 bypasses that. Its structure-insensitive design allows it to cut through the noise of ground cover and uneven canopy structures, focusing directly on the physiological health of your target crop. We've seen real-world examples where vineyard managers found NDVI maps messy, but SIPI2 better picked out the vine canopy, revealing precise areas of lagging growth. This makes it ideal for early stress and disease detection. SIPI2 can pinpoint physiological changes before they're visible, helping you intervene sooner. A study on palm groves, for instance, found that combining SIPI2 with other indices and machine learning achieved over 96% accuracy in detecting diseased trees. Nutrient status assessment. Nutrient deficiencies often impact leaf pigments. While not a direct nutrient quantifier like some specific indices, SIPI2 serves as an excellent general stress indicator that can flag potential nutrient imbalances in citrus, apple, and mango trees. Moving to rice fields, we have a different environment. Uniform, monoculture canopies, often with a flooded background. While nitrogen management is critical for rice and red edge indices like NDRE often excel here, SIPI2 still plays a valuable role. It can assess overall crop health and stress by tracking changes in the carotenoid-to-chlorophyll ratio. An increase in SIPI2 could signal stress from pests, diseases, or abiotic factors. Here's the critical point for rice. While NDRE might be your primary tool for quantifying nitrogen, SIPI2 acts as a powerful secondary or diagnostic tool. Why? Because research has shown SIPI2 can be uniquely sensitive to phosphorus deficiency, especially in later growth stages. Imagine using NDRE for nitrogen, but then seeing high SIPI2 values. That could flag a phosphorus issue that NDRE might miss. This multi-index approach provides a more comprehensive picture of your crop's health. So when do you use SIPI2? It all comes down to your monitoring objective, the crop type, and its growth stage. For orchards and vineyards, SIPI2 is a primary index for early stress, disease detection, and delineating management zones, especially where background vegetation is an issue.